Okay, this is going to be the first video of this course on algorithms, and it's going to cover chapter 1 in the book, The Introduction to the Design and Analysis of Algorithms by Levitin. Okay, so we're going to start off with just some basic discussions of what is an algorithm and why study algorithms. So an algorithm is nothing more than a step-by-step way of doing things. Okay, so that's one definition. Okay, we can say a step-by-step way, say, of solving a problem. Okay, one thing that we can say. The book defines it as a sequence of unambiguous instructions for solving a problem. Okay, and the unambiguous is important. We'll talk about that more in a second. Okay, so when you're looking at an algorithm, there's some things that you have to keep track of. Okay, you have to clearly define what problem you're trying to solve. You have to, as part of that, you have to give a range of possible inputs or possible problem types that can be solved with this problem. Okay, and then you have to give an unambiguous step-by-step way of doing things. Okay, and unambiguous here just means that it can't be open to interpretation. So, for example, a step of the algorithm shouldn't be something like, if it's warm, turn on the air conditioning. The reason being, warm is ambiguous. Warm to me is probably 70 degrees, where warm for somebody else may be much, much higher than that. Okay, so you have to make sure that you're clear in how you specify things. Okay, so this whole idea of the non-ambiguity really has to be important. We've seen this in our coding, that code is very literal and it's not open for interpretation. Okay, so the same algorithm can be written in several different ways. Okay, we'll go through some of the ways as we go through this class. In addition, you can have different algorithms to solve the same problem. Okay, some are more efficient than others, or you may prefer them for whatever reasons you may have. Okay, so again, there's a figure 1.1 gives this picture of moving from input into the computer. The computer then takes the algorithm and implements it with the input to give the output. And that's really what you're doing. That's where it's coming from. Okay. So one of the examples they give here are different ways to come up with the greatest common divisor of two numbers. Okay, to show that the same problem can be solved in different ways. Okay, and the first way they give is Euclid's algorithm. Okay, and you see already that there are two ways they're showing that. Okay, so the first way is more of a narrative. Okay, so make something bigger here if I can. So it's something like step 1. We're going to say if n, and I should have specified before, this is the GCD of m and n, two numbers. Okay, so if n is equal to 0, we're going to return the value of m. Let me type it correctly. The value of m as the answer. Stop. Okay. Otherwise, we're going to proceed to step 2. Okay. So step 2 then is going to be divide m by n and assign the value of the remainder of this operation, call that r, or remainder, call that value to r. Okay. We then go to step 3, where we're going to assign the value. It's fun. It's Monday when I'm doing this. Assign the value of n to m and r to n, and then go to step 1. Okay. So that's basically how that's going to operate. Okay, and that's the more of the English explanation of it. Okay. There's also an explanation that we're going to call pseudocode. And pseudocode is going to look like this. And I don't have exactly all the tools to make this look perfect. I don't have my iPad with me to run this from, but we'll get the idea. Okay. So it starts And this is going to be our preferred way. So this is going to be the Euclid algorithm. It's going to take an M and an N as its input. Okay. We're going to put some comments at the top. We're going to say that this computes the GCD of, we're going to do it this way, of M and N. So we're saying exactly what we're doing by Euclid's algorithm. Okay. We're going to specify our input precisely. Okay. It's going to be 2 non-negative, not both 0. Okay, one can be 0, they both can't be 0. Integers, M and N. It's a little bit wider. Okay. So those are the problems for which we can run this algorithm. The output is going to be the greatest common divisor of M. Okay. So in our pseudocode, and we'll get into some more examples as we go, we can start, or we can do basic structures, like from our coding. So we can say while N does not equal 0, do. Okay. So this is similar to the while loops that we've done in both Java and in Python. And then it's going to be, as long as this condition is true, we're going to keep spinning around. And when it's no longer true, then we're going to stop. Okay. And then we're going to have an R, and they use the left arrow, which I'm going to approximate like that in text. But if you're drawing it, it's doing next the left arrow. Okay. We're going to get R being equal to the M mod N. Remember, the modulo operator is going to be the remainder. So you take M divided by N, whatever is the whole number remainder. Okay. And then we're going to set M to N. And we're going to set N to R. Start the whole thing over again. Okay. And then and it's kind of like Python in that the structure of this block are determined by the spacing. Okay. So then we're going to return M as our answer. Okay. So both of these algorithms are exactly the same. They not exactly the same. They are representations of the same algorithm. Okay. One's the plain English and one's the pseudocode. Okay. You could also write a program in whatever language that would be another expression of the same algorithm. Okay. So the other algorithms that they give us here for the same problem is the consecutive integer checking algorithm. So that one is step 1, assign the value of the minimum of M and M to T. And then step 2, divide M by T. If the remainder of this division 0, go to step 3. Otherwise, go to step 4. In step 3, we divide N by R. If the remainder of this division is 0, return the value of T as the answer and stop. Otherwise, you go to step 4, where you decrease the value of T by 1 and go back to step 2. Okay. And that one, as it says here, does not work if one of the inputs is 0, but otherwise it solves the same number of problems. And then there's finally the middle school procedure for the GCD, where you do the prime factorization. So step 1 is find the prime factors of M, and step 2 is find the prime factors of N. Step 3, you identify all the common factors in the 2 prime expansions found in step 1 and step 2. Okay. And then finally, you compute the product of all of the common factors and return it as the greatest common divisor of the numbers given. Let me give an example of that. Okay. So again, those are 3 different techniques for doing exactly the same thing. Okay. So, and the book gives some other examples, but that's the basic idea there. Okay. So that's all getting us to this idea of what is an algorithm. Okay. The next thing we move to, so I'm moving into the next section of the textbook now, into 1.2, and that's going to be the fundamentals of how we're going to solve a problem using an algorithm. Okay. So let me clear all this stuff. start again here. So there's some steps that we have to take here. Okay. So we have to hear that we have to consider algorithms to be procedural solutions to problems. Okay, so they're not answers. They're not the answer to a problem. They're a way to get an answer. Okay, so they're procedural solutions, not actual solutions. Okay, so from that, we're going to go through the steps we normally going to have to go through. Okay, and these should be pretty clear. We're going to start with understanding the problem. Okay, this is pretty basic. If I ask you to give me the Wacom of a number, which I just made up, there's no way you can do that unless you know what that means, right? You have to have a definition. So you have to understand the problem you're trying to solve. Okay. So that's the very first step. Okay. Then you have to know what kind of input you're looking at, what needs to happen as far as that goes. Okay. So once you understand the problem you have at hand, the next thing is to ascertain the capabilities of the computational device that you're going to be using. Okay. This could be your brain, could be pencil and paper, could be a calculator, could be a different computer language. Whatever it is, there are some algorithms that are easier to work in our heads and some that are easier to turn into programs. Okay. So that's what we're talking about with that. Okay. So once you've done that, the next step you have to decide is to choose between exact solutions and approximate solutions. Okay. So sometimes it turns out that close is good enough. You know, that within a certain range, we don't have to worry about getting it exactly right. Okay, so sometimes the approximation will be good enough and it will be so much faster and so much more efficient that it'll be worthwhile. Other times you need the exact solutions, and it's important that you get the exact solutions. So up front, you have to know that. Okay. The next thing is kind of what the whole book's going to be, at least the whole next 4 or 5 chapters. We're going to figure out what algorithm design techniques that we can apply. Okay, so what strategy, what paradigm we're going to use. Okay. So the next step is going to be once we decide that, and again, we're going to get those starting in chapter 3. We're going to do designing an algorithm and the data structures. You just came from a data structure course, so you should be familiar with that idea. There are some data structures that allow for certain maneuvers or certain things to be done to them, certain techniques, okay, that are better or worse. Okay. And then other things aren't really related to the steps, but just kind of what we talked about before, they're reiterating it here, that you have to have a method to specify the algorithm. Okay. And that could be just the natural language. That's the step 1, step 2. Instead, okay. It could be the pseudocode, which I gave an example of, okay, which is a mix of language and programming-like kinds of structures that we can do. Okay. You can also do flowcharts. I'm kind of a fan of flowcharts myself, but I'm kind of old school on that. But we don't use those so much anymore, but they certainly work. Okay. So once you've specified the algorithm in some way, of course, we can also do a computer program as another specification. But you then have to prove that the algorithm is correct. Okay. And that can be a bit tricky. So you don't want to put it out into the world if it's not going to be correct. Okay. And it should be correct for all the input you say it's going to be good for. Okay. So if, for example, your algorithm doesn't work for negative numbers, your input should specifically say not for negative numbers. And if it's a program, it should test to make sure you're not giving it negative numbers. Okay. So The next step after you've done that is really to analyze the algorithm. And here we're looking for two different things here. The first, well, actually, there are three factors here. Efficiency. And that comes down to time efficiency. Time efficiency is how long it takes to calculate on whatever computational device you're doing, okay? And then we have space efficiency. We talked about that a little bit before, just how much paper would it take if you're doing it on paper, how much memory would it take, those kinds of things, okay? Another characteristics, these are more characteristics of our algorithm, whenever possible. Simplicity is best. Okay, think of Occam's razor, that if you're given possible solutions to a problem, the one that's simplest is probably the one that's correct, okay? Which I think makes some sense. I'm also reminded of Einstein's quote that our solution should be as simple as possible, but no simpler, okay? So unless there's a great advantage to adding complexity, and there's usually not, you want it to be as simple as it can be. But again, if it's too simple, it's not going to do the job, okay? So simplicity, simple is better, okay? And the other thing, the other characteristic we're looking for here is that generality is better. Okay, the more problems we can solve, the bigger the range of inputs we can solve. Okay, again, you have to balance that with simplicity though. So there's always pros and cons there. Okay. So we can then code up our algorithms. We can test them out. We can see if they work. We can see if we're getting good solutions. Okay. So these are all some things that we can consider. Let's go on to the maybe last. Nope, come on. Next to last section. Okay. Important problem types. So these are the kinds of problems that computer scientists are always looking at. Okay, that are helpful and that are worth improving if you can. Okay, we have sorting, we have searching. I don't type in, you can listen. We have sorting, we have searching, we have string processing, text searches, things like that, or text changes. Okay, we have graph problems. There are many problems in the world that we can turn into a graph, and by graph we're talking about graph as in, you know, we have the vertices. I assume you saw these in data structures, and then you have all that stuff. Not that kind of graph. Okay, this kind of graph. Okay. Combinatorial programs, which may still give you anxiety from the finite mathematics course that we started with. Geometric problems, numerical problems. Okay, those are all kinds of problems that we have. Okay. So when we go through those, and we'll go through all those, and you can go through each one. Sorting is a big deal. It's, you know, you're rearranging items of a given list or some given data structure in either a decreasing or non-decreasing fashion. Okay, and we do this because it's faster to search, and we can look for repetitions, all kinds of things. Okay, so it's an important problem, and you've probably seen sorting somewhere along the way, but we'll talk about it a whole lot more in this course. One of the properties that we like in our sorting algorithm is one called stability. Okay, so stability means if we have, for example, 7, 3, 4, 3, 10, and we sort it. If when we're sorted that this 3 is this 3, and that 3 is that 3, and they don't get switched around, we call that a stable sorting algorithm. It's advantageous because it's one less move around in memory. Okay. So that's one of the things that we talk about with our sorts. We also talk about an algorithm, sorting algorithm is said to be in place if it does not require extra memory. Okay, so if you're storing in memory, and I'm drawing with a mouse, so it's worse than my normal handwriting. If you're storing, you know, values in here, or whatever they are, if you can rearrange these without having to write them someplace else, okay, then that's called in place. And that's going to save you space. Okay, for sure. Okay. It then goes through the idea of searching, how that's an issue where you're searching for a search key, string processings where you're going through and making some change to text strings, okay, string matching, things like that. Graph problems, it talks about, it gives us a preview of some problems we'll talk about later, traveling salesman problem and the graph coloring problem. And combinatorial problems we've talked about before, geometric problems and numerical problems, okay? And then we get to this idea of the data structures, okay? The basic kinds of data structures that we can have, okay? And again, you should be coming out of this class, so you should be okay with this. Let's take a look here. So it starts, we have linear data structures. Okay, this is going to be an array, it's going to be a list in Python, things like that, okay? Those typically have an index, we can get to them, you know, things like that. We also have other things, which I assume you talked about data structures, like linked lists, which are not index-based, but positional-based, doubly linked lists, we have stacks, we have queues. All of those things are all going to be considered linear data structures, okay? We then have graphs. I assume you also talked about in data structures. Again, I just gave the simple drawing of that a minute ago. So you have those kinds of data structures, which both either a graph and also in the matrix representation or the adjacency graph, or the adjacency matrix of a graph, which we'll be looking at, which will be very useful. Remember, graphs can be weighted or not, which means each edge can have a weight assigned to it or not, okay? We have trees, okay, which is a connected acyclic graph, which we'll talk more about as we go through. We use trees for different things, okay? Then finally, we have sets. Remember, a set has the property that there are no repeats, basically. Everything's unique, all unique elements. And then we have the dictionaries, also called associative arrays, and that's the key value pairs. That's how it's stored, okay? So these data structures are important, again, as we look at our problems. They give us a way to structure the data. So I think it's called that. So by picking one or the other, they'll have strengths or weaknesses. Okay, so for example, if you're trying to do a search and typically something like a linked list is not a good option because you can't get directly to everything. A linked list, you have to begin at the root and go through every element, okay? So it's not always a good choice for that. So different problems lend themselves to different data structures. Okay, so we'll have to think about that as we go along. Okay, so that's really the highlights of chapter 1. Okay, so there'll be a problem set for this. And certainly if you have questions, let me know. But yeah, I think that's it. That should get us started. Make sure you read through it. I think probably the best strategy, which is kind of late for me to tell you this now, but in general, read through the chapter first, make notes on it yourself with what questions you have. Watch the video, see what I have to say about it, and see if you have further questions. Either the questions were answered or the questions were not answered. But in either case, you can post those in the forum or come to the weekly Zoom meetings and we can talk about that. Okay. So that's chapter 1. Next week, we'll be doing chapter 2, which is the fundamentals of analysis of algorithm efficiency.